The year is 1911. A young German Earth scientist named Alfred Wegener is thinking about how continents and oceans have changed over geologic time. His ideas are revolutionary because the Earth's surface is thought to be fixed, permanent, and unchanging. Little did he know that his concepts would someday become the basis for the modern theory of plate tectonics.
My theory about drifting continents has not been well received. The others call it preposterous, foolish, outright lunacy. Indeed, I have proof, but still, it may not be enough. I am confident that someday the efforts of scientists will succeed in uncovering all the necessary evidence. Only then will my theory be embraced and accepted as the truth.
In 1930, while still refining his theory, Alfred Wegener died tragically on an expedition to Greenland. An entire generation of scientists would follow before his ideas were taken seriously. The evidence he looked for eventually was discovered. It came from the oceans, from the continents, and from views taken high above the Earth's surface. Inspired by Wegener's hypothesis, plate tectonics has emerged as one of the greatest scientific theories of the 20th century. Look closely at the coastlines of eastern South America and Western Africa. The way they would fit together is certainly intriguing. Wegener thought so too. He was curious about reports of 250-million-year-old Glossopteris ferns and Mesosaur reptiles that had been dug out of rocks in South America, Africa, and from scattered locations across the southern hemisphere. Other rocks contained signs of widespread glaciers, a clue that Wegener interpreted as evidence for vast ice sheets in areas now covered by tropical forests. The only explanation he concluded was that the continents had once been joined together over an area that once straddled the South Pole. He went even further and postulated that this large landmass had somehow broken up and then moved apart. He called this giant supercontinent Pangaea, meaning all lands. By proposing the concept of continental drift, Wegener's bold ideas did not fit in with the accepted theory of permanence, the notion that the continents and oceans were as old as the Earth itself. He believed that the lighter, less dense crust of the continents floated like blocks of ice on the more dense, stationary crust of the ocean floor. Wegener based his conclusions on many lines of evidence. From matching fossils and sedimentary rocks, he theorized the existence of Pangaea. And from the buoyant properties of ice flows, he suggested a mechanism for the movement of continents. Despite his findings, little was known about the Earth's crust during the 1920s. Almost 20 years after his death, new technologies emerged that began to fill the gaps that Wegener hoped would someday support his theories. By 1950, oceanographers had begun using echo sounding and sonar to map the details of the ocean floors. There, they discovered enormous mountain chains of fractured crust, far more extensive than any known on land. The rugged peaks appeared to wind down the centers of ocean basins like stitches on a baseball. Scientists named them mid-ocean ridges, topographic features which encircle the globe for a distance of 74,000 kilometers. In other places, they found steep volcanic cones called seamounts and deep, arc-shaped trenches that border the edges of continents and island chains. The ocean floor, it seemed, was an exceedingly rugged landscape, a bizarre and mysterious terrain of which Wegener had little knowledge. As oceanographers were busily mapping the sea floor, geophysicists had new evidence of patterns that were marked by the locations of thousands of earthquakes and volcanoes. Even more puzzling were the patterns of magnetism in volcanic rocks that flanked the mid-ocean ridges. Further study revealed that these rocks were far younger than anyone had imagined. By the late 1960s, it was clear that enough evidence had been gathered to confirm Wegener's theory of continental drifts. The ridges, trenches, distribution of earthquakes and volcanoes, and even the patterns of relatively young oceanic crust were all the results of shifting continents. Today, all this evidence has been combined into the modern theory of plate tectonics. Let's take a closer look. The Earth's outer crust, or lithosphere, is divided into 9 major tectonic plates that cover the Earth like pieces of a jigsaw puzzle. They're thousands of kilometers wide, yet only 80 kilometers thick. Unlike the continent-shaped blocks that Wegener described, tectonic plates are outlined by ridges, trenches, rifts, and other major cracks in the Earth's lithosphere. The plates shown here are usually named for the continents they carry, even if they consist entirely of oceanic crust. Tectonic plates, like pieces of cooling lava, are rigid but constantly moving slabs of crust, splitting, fusing, and bumping against each other. The arrows indicate their relative motions. Where plates interlock, intense geologic activity such as earthquakes and volcanoes are most likely to occur. The puzzle of the continents works like this. Plate edges meet along 3 types of boundaries: divergent, convergent, and transform plate boundaries. The first type is called a divergent plate boundary and is found along mid-ocean ridges where plates are actively separating. This process is called seafloor spreading because the crust of the ocean is literally spreading apart. Here, molten rock oozes out onto the ocean floor and then cools along a central valley within the mid-ocean ridge system. As the older volcanic rock is wedged apart, younger molten rock welds up to fill the widening gap between the valley walls. The rock then cools to form new oceanic crust. Divergent plate boundaries can also be found on land, where the end result is the birth of an ocean basin. Beneath the rigid lithosphere lies a weak, plastic-like layer called the asthenosphere. As heat from the asthenosphere bulges upward, it stretches and breaks the overlying crustal plate into an elongated crack called a rift valley. If spreading continues and the growing rift reaches a coastline, seawater may flood the valley to form the beginnings of a new ocean basin. The circular movement of heat or convection deep in the asthenosphere drives the movement of the new sea floor, like a conveyor belt, wedging the plates apart at an average rate of 1 to 2 centimeters a year. These views from space capture the process in action. East Africa and Saudi Arabia are being wrenched apart by seafloor spreading. The Red Sea and Gulf of Aden are among the world's youngest ocean basins. Today, geophysicists use computers to simulate convection in the asthenosphere. In this model, you can clearly see the fluid-like currents that drive the motion of the ocean floor and the continental crust. Oceanographers are also eyewitnesses to the bizarre environment at mid-ocean ridges. There they find shimmering hot springs, deposits of sulfide minerals, and strange forms of life that cling to the warm waters around deep-sea vents like these. In the North Atlantic, the mid-ocean ridge rises above sea level, dividing the island nation of Iceland along a major plate boundary. These faults form the dividing line between the west-moving North American plate on the left and the east-moving Eurasian plate on the right. Each day, the Rift Valley stretches, the plates diverge further, and the Atlantic Ocean widens, all at the rate of a growing fingernail. For hundreds of years, humans have taken advantage of these forces. The capital city of Reykjavik gets its energy from geothermal wells that tap the storehouse of heat that simmers along divergent plate boundaries. The second type of plate boundary is called a convergent boundary. It's a zone along which plates collide. Converging plates produce mountain chains, volcanoes, earthquakes, and in many cases, ocean trenches. The first example shows the collision between an oceanic and a continental plate. Here, off the coast of Chile, part of the Pacific plate joins the South American plate along a deep submarine trench. As the plates come together, the dense volcanic rock of the oceanic crust begins to sink beneath the lighter granitic rock of the continental crust. This line of collision is known as a subduction zone. Here, the descending slab is recycled back into the upper mantle, where it's remelted and begins to rise along deep fractures to form volcanoes at the surface. Earthquakes occur frequently along the plane that's defined by the slab of sinking crust. The 1980 eruption of Mount St. Helens resulted from the subduction of the oceanic Juan de Fuca plate beneath the continental North American plate. Mount St. Helens, like its neighboring peaks in the distance, is part of a chain of towering volcanoes that form the Cascade Range of the Pacific Northwest. Where two equally dense continental plates converge, neither can be subducted, so the crust is warped upwards along the line of collision. Convection currents in the asthenosphere drive the movement of the overlying crust, piggybacking the plates toward each other like trains bound for a head-on collision. Over a period of millions of years, crashing continents can rumple the Earth's crust upwards to form folded mountains. And finally, plates that neither push nor pull against each other are known as transform plate boundaries. Along transform boundaries, plates slip in a side-by-side motion along a crack or fault. Over time, stress builds as the plates slowly grind past each other. When the crust can no longer withstand the built-up stress, energy is released and an earthquake occurs. To Californians, faults and transform boundaries are facts of life. The famous San Andreas Fault forms a striking gash across the desert landscape, a 1,000-kilometer-long seam that divides California between two major tectonic plates. The crustal movement along the San Andreas displaces the Pacific plate northwest relative to the North American plate. In places, the fault locks and then slips abruptly as it did during the earthquake that shook the San Francisco Bay Area in October of 1989. In an instant, two crustal plates lurched 1.5 meters past each other, leaving 61 people dead and billions of dollars in damage. Perhaps the most intriguing piece of the plate tectonic puzzle is the occurrence of earthquakes and active volcanoes that lie thousands of kilometers from plate boundaries. Located smack in the middle of the Pacific Plate, Kilauea volcano on the big island of Hawaii sits atop a hot spot that's rooted deep within the Earth's mantle. As magma burns its way through the oceanic crust to the Earth's surface, it builds a new volcano. Like a conveyor belt that rides atop a burning flame, the Pacific Plate marches forward over the stationary hotspot, leaving a trail of progressively older seamounts to mark its former position. Alfred Wegener, of course, did not live to see his theory of continental drift evolve into the science of modern plate tectonics. If he had, he would have been astounded at the technologies used by many scientists to confirm his theory. He would have been impressed by models of convection in the asthenosphere and by computer-generated reconstructions of the supercontinent he named Pangaea. He would have been intrigued by the discoveries of bizarre life forms and underwater volcanoes that are concentrated near hotspots and rifting plates. And he would have marveled at space-eye views of the Earth's continents and been impressed by the bewildering submarine landscapes that have resulted from the spreading, shifting ocean floors.
Continental drift, rift valleys, volcanic eruptions, faults and compressions, earthquakes. They all are undoubtedly connected causally on a grand scale. All Earth sciences must contribute evidence towards unveiling the state of our planet in earlier times. And they, the truth of the matter, can only be reached by combining all this evidence.
Alfred Wegener knew that his theory of continental drift was incomplete. But he had confidence it would stand the test of time and become the solution to the puzzle of the continents.